To calculate the correct resistance on a transformer without a load, you can use the formula resistance equals primary voltage squared divided by transformer power times 2. Let's apply this formula to an example. Assume the primary voltage is 480 volts and the transformer power is 150 volt amps. The calculation is as follows: resistance equals 480 volts squared divided by 150 volt amps times 2. This simplifies to resistance equals 230,400 volts squared divided by 300 volt amps, resulting in a resistance of 768 ohms. Therefore, the correct resistance on the transformer without a load is 768 ohms. This calculation helps verify the integrity of the transformer's primary winding. A significant deviation from this calculated resistance could indicate a fault, such as shorted windings or insulation breakdown. When performing resistance measurements on a transformer, it's important to use an appropriate measuring instrument, such as a digital multimeter or an ohmmeter with sufficient accuracy and resolution. Ensure that the transformer is de-energized and isolated from the power source before making any measurements to prevent electrical shock or damage to the equipment. Also, discharge any stored energy in the transformer's windings to ensure accurate readings and prevent injury. The temperature of the transformer windings can affect the resistance measurement, so it's best to perform the test at a stable ambient temperature. Record the ambient temperature during the test to allow for temperature correction if necessary. It's also important to consider the transformer's nameplate data, which provides valuable information about its electrical characteristics, including voltage, power, and impedance. This information can be used to verify the accuracy of the calculated resistance and to identify any potential problems. In addition to the resistance measurement, it's also recommended to perform other tests, such as insulation resistance tests and turns ratio tests, to comprehensively assess the condition of the transformer. Insulation resistance tests measure the resistance between the transformer windings and ground, while turns ratio tests verify the correct turns ratio between the primary and secondary windings. These tests can help detect insulation degradation, winding faults, and other potential problems that may not be revealed by a simple resistance measurement. Understanding the principles of transformer operation and testing is essential for electrical engineers and technicians involved in the maintenance and troubleshooting of electrical power systems. By performing regular tests and inspections, potential problems can be identified and addressed before they lead to costly downtime or equipment failure. The formula resistance equals primary voltage squared divided by transformer power times 2 is derived from the basic principles of electrical power and impedance. The transformer power, measured in volt amps, represents the apparent power that the transformer can deliver. The primary voltage is the voltage applied to the transformer's primary winding. The resistance, measured in ohms, represents the opposition to current flow in the transformer's primary winding. The formula assumes that the transformer is operating at its rated voltage and frequency and that the load is purely resistive. In practice, the load may have a reactive component which can affect the accuracy of the calculated resistance. However, for most practical applications, the formula provides a reasonable estimate of the transformer's resistance. When using the formula, it's important to use consistent units of measurement. The primary voltage should be expressed in volts, the transformer power should be expressed in volt amps, and the resistance will be expressed in ohms. If different units are used, the formula will not produce accurate results. For example, if the transformer power is expressed in watts, it must be converted to volt amps before using the formula. The relationship between watts and volt amps is given by the power factor, which is the cosine of the angle between the voltage and current waveforms. For a purely resistive load, the power factor is 1 and the watts are equal to the volt amps. However, for a reactive load, the power factor is less than 1 and the watts are less than the volt amps. In addition to the resistance measurement, it's also important to consider the transformer's impedance, which is the total opposition to current flow in the transformer's windings. The impedance is a complex quantity that consists of both resistance and reactance. The reactance is the opposition to current flow due to inductance and capacitance. The impedance can be measured using an impedance analyzer or calculated from the transformer's nameplate data. The impedance is an important parameter for determining the transformer's voltage regulation and short-circuit current. The voltage regulation is the change in secondary voltage from no load to full load. The short-circuit current is the current that flows through the transformer's windings when the secondary terminals are shorted. The impedance helps to limit the short-circuit current and protect the transformer from damage. When testing a transformer, it's also important to consider the safety precautions. Transformers can store large amounts of energy, which can be hazardous if not handled properly. Always de-energize and isolate the transformer from the power source before making any measurements or performing any maintenance. Use appropriate personal protective equipment such as gloves and safety glasses to protect yourself from electrical shock and other hazards. Follow all applicable safety regulations and guidelines when working with transformers. In summary, calculating the resistance of a transformer without a load involves using the formula resistance equals primary voltage squared divided by transformer power times 2. This calculation provides a valuable check on the transformer's condition and can help identify potential problems. Remember to use consistent units of measurement, consider the temperature of the windings, and follow all applicable safety precautions. By understanding the principles of transformer operation and testing, you can ensure the safe and reliable operation of electrical power systems. The no-load test, for which this resistance calculation is a part, is a core method to understand a transformer's core losses, which are further broken down into hysteresis and eddy current losses. Hysteresis losses are due to the energy expended in repeatedly magnetizing and demagnetizing the core as the alternating current flows. Eddy current losses arise from circulating currents induced in the core material by the changing magnetic field. These currents dissipate energy as heat due to the core's resistance. During a no-load test, the transformer's secondary side is left open-circuited while the primary side is energized at its rated voltage. Input power, voltage, and current are carefully measured. Because the secondary side is open, the current drawn by the primary is very small, typically a few % of the full load current. This small current primarily supplies the core losses, while the copper losses in the windings are negligible. The input power measured during the no-load test is essentially equal to the core losses. The equivalent circuit parameters representing these core losses, namely the core loss resistance and magnetizing reactance, can be determined from the test data. The core loss resistance represents the energy dissipated as heat due to hysteresis and eddy currents. The magnetizing reactance represents the inductive reactance of the primary winding when the secondary is open-circuited. To accurately measure the input power during the no-load test, a wattmeter with sufficient sensitivity and accuracy is required. The wattmeter should be connected in the primary circuit, and care should be taken to ensure that the voltage and current ranges are appropriately selected. The readings from the wattmeter, voltmeter, and ammeter are used to calculate the core losses and equivalent circuit parameters. The no-load test is typically performed at the transformer's rated frequency. However, the test can also be performed at different frequencies to investigate the frequency dependence of the core losses. The core losses generally increase with increasing frequency, but the relationship is not always linear. The no-load test is a valuable tool for assessing the quality of the transformer core and identifying potential problems. High core losses can indicate defects in the core material, such as laminations that are not properly insulated or air gaps in the core. These defects can lead to increased heating, reduced efficiency, and premature failure of the transformer. In addition to measuring the core losses, the no-load test can also be used to determine the transformer's magnetizing current. The magnetizing current is the current required to establish the magnetic flux in the core. It is typically a small fraction of the full load current, but it can be significant in large transformers. The magnetizing current can be affected by the core material, the air gap in the core, and the applied voltage. A high magnetizing current can indicate saturation of the core, which can lead to increased distortion of the voltage and current waveforms. The no-load test is a relatively simple and inexpensive test to perform, but it provides valuable information about the transformer's core and windings. It is an essential part of the routine maintenance and testing of transformers in electrical power systems. The open circuit test is another name for this and is often used interchangeably. In addition to the formula provided initially, which offers a simplified approach to understanding resistance, it's crucial to understand that a direct resistance measurement using an ohmmeter across the primary winding without energizing the transformer won't directly correlate to the calculated resistance derived from the voltage and power formula. The ohmmeter will measure the DC resistance of the copper wire in the primary winding, which is typically very low, often less than an ohm, while the calculated resistance using the formula reflects the impedance the primary winding presents to the AC source at the rated voltage and frequency. It is important to remember that a transformer relies on alternating current to operate correctly. The changing magnetic field created by the AC current in the primary winding induces a voltage in the secondary winding. This induction process is dependent on the frequency of the AC current. A DC voltage, which is what an ohmmeter uses to measure resistance, will not create this changing magnetic field, and therefore the transformer will not function as intended. Instead, the ohmmeter will only measure the resistance of the copper wire. This is why the formula incorporating voltage and power is used to estimate the effective resistance under normal operating conditions. The DC resistance can still be useful for detecting shorted turns in a winding, where a significantly lower than expected resistance reading can indicate a problem. The formula, again, is a reflection of the impedance the transformer presents to the AC source at its rated voltage and frequency. Formula is derived from fundamental electrical principles. The power delivered to the primary winding is equal to the voltage squared divided by the impedance. In the no-load condition, the power is primarily consumed by the core losses. By measuring the input voltage and power, and knowing these values, we can calculate the effective impedance, which is predominantly resistive in the no-load condition. The turns ratio of the transformer is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. This ratio determines the voltage transformation ratio of the transformer. If the primary winding has more turns than the secondary winding, the transformer is a step-down transformer, meaning that the secondary voltage is lower than the primary voltage. If the primary winding has fewer turns than the secondary winding, the transformer is a step-up transformer, meaning that the secondary voltage is higher than the primary voltage. The turns ratio is an important parameter for matching the voltage levels of different circuits. For example, a step-down transformer might be used to reduce the voltage for a high-voltage transmission line to a lower-voltage distribution line. The turns ratio can be measured using a turns ratio tester, which applies a low-voltage AC signal to one winding and measures the voltage induced in the other winding. The ratio of the two voltages is equal to the turns ratio. The turns ratio should be checked periodically to ensure that it is within the specified tolerance. A significant change in the turns ratio can indicate a problem with the transformer windings, such as shorted turns or open circuits. The insulation resistance of a transformer is the resistance between the windings and ground or between different windings. The insulation resistance is a measure of the quality of the insulation material. High insulation resistance indicates good insulation quality, while low insulation resistance indicates poor insulation quality. Poor insulation quality can lead to insulation breakdown and failure of the transformer. The insulation resistance should be measured periodically using a megometer, also known as a megger. The megometer applies a high-voltage DC signal to the insulation and measures the resulting current. The insulation resistance is calculated from the voltage and current. The insulation resistance should be measured at different voltage levels to assess the condition of the insulation over a range of voltages. The insulation resistance should be measured with the transformer de-energized and isolated from the power source. The temperature of the insulation can affect the insulation resistance, so it's best to perform the test at a stable ambient temperature. The test is a diagnostic measure of the dielectric strength of the winding insulation.